Man, what am I doing?
This video was recorded in front of a live studio audience. And welcome back to another exciting episode of Mr. Bell Physics, where today we have a live studio audience. Make yourself heard! Yeah, it is a little bit weird, but we're going to do it anyways. Welcome to part 3 of our kinematics. Actually, no, this is not part 3 of the kinematics. This is just an example problem. Part 3 is going to be a little bit simpler than this, but I have been getting a few requests to do an example problem from our study guide for our midterm, specifically number 12 on the study guide, which reads, a soccer ball is kicked from the top of a 12-meter hill with an initial speed of 18 meters per second and at an angle of 25 degrees above the horizontal. And then there's a bunch of stuff like determining velocity, which we'll take on part by part. The number one thing to do when starting this type of problem is to draw it out. So I'm going to take a marker and I'm going to draw this out. So what I know is that I am kicking a ball mostly horizontally, but also with a small vertical component off of an elevated surface. So what I need to do is I need to draw an elevated surface. Like so. Okay. This has a height of 12 meters. And I know that I kick my soccer ball at an angle. That angle is 25 degrees. And it is going to go over a certain height and distance until it eventually hits the ground somewhere around here. Now, in order to do this problem, there's a lot of things that I need to consider. Specifically, I need to consider the individual components of this velocity vector. This is a two-dimensional vector, so therefore I need to break it up into its x and y components before I can do any math. Then I need to use my kinematic equations to determine what the best strategy is to solve a problem like this. So let's start off by breaking that vector into its components. So as I will hopefully have a video on this sometime very quickly after this uploads, there are two main formulas that we're concerned about when breaking a vector into its components. Specifically, we are worried about x equals r cosine theta and y equals r sine theta. But what do these equations actually mean? Okay, what if you need a refresher on that? Good question. Okay, let's break it down. Let's say I have a resultant vector like this, which we're going to call r. That vector is in two dimensions. It's in the x and y plane at the same time. Unfortunately, as great as Newton's equations are, they're not great enough to be able to do math with this number right now. Instead, we need to break it up into components like so, where we have an x component in blue there, and a y component in red. So, y is going to be in red, x is going to be in blue for our purposes here. Okay. Now, there is a known angle here, down here, called theta. That is going to be our 25 degrees from the problem. And in order to solve for the x component of our resultant vector, in this case our velocity, we use this top formula, r cosine theta. So r in this case I believe was 18. Yes, it was. So I'm going to also just label that on my diagram here, that this is 18 meters per second. So it'll be 18 times the cosine of 25 degrees to solve for x, and it'll be 18 times the sine of 25 degrees to solve for y. Without having those values, I cannot solve this problem. So before you even start looking at kinematic equations, before you even start trying to figure out what you're supposed to be doing, always make sure that you break up this vector into its x and y components. So let's go ahead and do that real quick. So take your screenshots now. I'm going to erase this in a second. That should be enough time. So what we know is that our vector has a resultant value of 18 meters per second and an angle of 25 degrees. Let's start off with solving for our x component. X is going to be equal to r cosine theta. So, in order to solve for x, I'm going to plug in my numbers. X is what we're trying to solve for. R is my 18. Cosine is just a function. And theta is going to be my 25 degrees. So when I do that on my calculator, I want to make sure that my calculator is in degrees mode, not radians mode, because that is a very common mistake that people will make. And live studio audience, when I do that on my calculator, tell me what I get. 16.31. Fascinating how that works. So when this all is done out, hold for applause, yes. When this all is done out, we got 16.31. This still needs a unit, because this is just the x component of v. So instead of thinking about like x, think about v sub x, okay, the x component of that initial velocity. So you can even think about it as vi x, if that is helpful. So the unit carries over. So velocity is always measured in meters per second. Therefore, this is also measured in meters per second. So that's well and good. We have x. Now let's do y. Y is equal to r sine theta. So we use the exact same logic we used before. We just plug in. Y, we don't know it yet, so y just stays as y. R, we know is 18, so we plug that in. Sine, our theta angle, 25. So again, when I do that in my calculator, I'm going to get VIY. And when I do that in my calculator, live studio audience, 7.607. Thank you very much. If you're going to clap the first time, clap the second time. Come on, guys. Okay. So 7.607 meters per second. So I'm actually going to make a note of that over on the side here. So VIY is going to be 7.607 meters per second. And VIX is going to be 16.31 meters per second. If you take a second to think about what's really going on here, this makes sense conceptually. If I'm launching it at a 25-degree angle, if I'm really thinking about if this is 0 and this is like 45, 25 is going to be somewhere like around here. Notice it is more horizontal than it is vertical, which means that my horizontal number, my x value, should be greater than my y value. If I'm going above 45 degrees, I know I'm going more vertical. Therefore, my y value should be the bigger number. So you can always kind of double check if you're doing it right by taking a second to think about common sense along the way here. So now that we have those values, we can actually start doing some math. So erasing the trigonometry math here. Give me a second. And all right. So if we think about our problem again, it might be useful for us to actually write down our kinematic equations. So we have 4 kinematic equations, and like I've stated previously, all 4 of them are correct at the same time. The tricky part about kinematic equations is that we had to figure out which one is the best for us right now. So figuring that out, it involves us basically looking at the equations and seeing what do we have, what do we not have. So let's write down these equations. So we have equation 1, which is V final is equal to V initial plus A times T. Equation 2, which is going to be V final squared equals V initial squared plus 2A change in X. Equation 3 is going to be change in X equals VI times T plus 1/2 AT squared. And then finally, we have equation 4, which is going to be change in X equals 1/2 parentheses VI plus VF times T. So automatically, we already have a lot of things to kind of work through here. Okay, it looks very intimidating, but I assure you it's really not that bad. the best way we can go about doing this is making our list of variables on the side here. So what else do we actually know about this? Well, right now, the only thing that we're really given is our x and y components, which is also solving for part A of the problem. We're asking for determine the horizontal and vertical components of the initial velocity. The next thing that they're asking for is how long does it take the ball to reach its maximum height? Now, when we think about what is actually happening here, we need to take into consideration both our x and y components, and the best way to do that, in my opinion, is making a table. So, over here, all the way at the side, I'm going to make my table of all my different variables. Okay, so I'm going to have x and y, and I'm going to have my displacement, my VI, VF, acceleration, and time. I make this whole table just to make myself a little bit more neat, a little bit more organized, because this math can get kind of messy kind of quickly. So, already I can fill in both my VIY and VIX because I calculated those values. But what I can also do is I can actually start to assume some of these values. So, let's start off with X. My total displacement in the X direction, I do not know yet. So that I'm going to leave blank. VI, I do know. That's 16.31. I solve for that. We'll write that down. That way I can erase it over here. When I'm really thinking about what's going on in the X direction, I'm essentially throwing something straight. Now, if I'm throwing something straight, and I think logically about it for a second, as both the person throwing it and the person receiving it, say I'm throwing a ball, or for example, in this case, a stuffed chicken nugget. By the time that I actually throw it towards my live studio audience, okay, this is Mr. Bell on camera throwing things at his students, okay, applause, thank you. By the time that it releases from my hand, and by the time that it hits my student's hand, the nugget isn't actually going to be speeding up at all. There's no acceleration happening here. So, it was a good catch. It was a good catch, okay? It totally did not hit her in the face. So, for legal reasons, that is. Okay. They took the revenge. Okay, so we're going to move that to the side. So, I wasn't ready for that. Yeah. Now we caught me off guard. Now we got me. Yeah, okay. So, acceleration in the x direction is going to be 0 because my velocity isn't changing at all. Okay, we're ignoring air resistance for our purposes here. So, if acceleration is 0, we know for a fact that acceleration is how velocity is changing over time. If acceleration is 0, that means that velocity can't be changing over time, which means both VI and VF must be 16.31. So that makes our life a little bit easier. Now again, at this point, I don't have enough information to solve for time yet, so time is going to be left blank. However, something that I am going to remember is that time is dimensionless. It is the only variable here that does not have an x or y direction. It will carry over for both and be identical for both. So, while I don't have enough information to solve for t in the x direction, I probably am going to have enough information to solve for it in the y direction if I actually start plugging everything in. So, let's see if I'm right. For y, our displacement will be our height. We don't know that yet. So, we're going to skip that. VIY, we do know, is going to be 7.607 meters per second. Skipping VF for now, we'll come back to that in a second. Acceleration here, we do have a number for that, and we know for a fact that it is caused by gravity. The acceleration due to gravity is always going to be 9.8 meters per second squared. The positive or negative, we're going to determine whether or not we use it based off of if we are slowing down as we go up or speeding up as we go down. Now, in this case, if I'm thinking about this, I know for a fact that my problems, I need a constant acceleration. So if I redraw this out over here, which I should still have some space for, a basic kind of arc of motion here, I really have two instances of acceleration. I have one where gravity is slowing things down, and one where it's speeding things up. Because of that, I can't actually find my whole time period yet. I can only find 1/2 of my time period. So because of that, I need to do a little bit more thinking here. Let's say I take yet another stuffed chicken nugget, the only one that I have left because all the others have been assaulted, essentially. If I were to toss this directly up into the air, like so, what you may notice is that at the very instant that it reaches its peak height, it stops moving for a second before it starts slowing back down and moving down again. Because of that, I can run with the assumption that at the very peak of my height, my vertical velocity, because remember, we're only caring about velocity up and down direction, not left and right, is going to be 0. Now, with this table as it is right now, and if we look over at our equations, I'm immediately drawn to look at equation 1. V final equals V initial plus acceleration times time. V final is 0. V initial is 7.607. A is going to be negative 9.8. T is unknown. We can solve for time. So, with that being said, let's actually solve for this. And again, I'm going to stay in red here just to make sure that people understand that the math I'm doing is in the y direction right now. So, the math I'm doing is in the y direction right now. So we're staying in red. So let's plug in our numbers. V final is 0. And that's going to be equal to V initial, 7.607, plus negative 9.8. I'm using negative 9.8 because I have to remember my soccer ball or chicken nugget or whatever projectile we want to use here is slowing down over time as it goes up. Okay, the further up it goes, the slower it is moving in the vertical direction. So it has to be a negative acceleration to accommodate for that. If I was speeding up, it would be a positive acceleration. I know that the magnitude of my acceleration here on Earth is always 9.8, but since I'm slowing down, I had to throw that negative in front of it. And then that's going to be multiplied by time, which I don't know yet. So solving this out doesn't actually seem too bad. Okay, it's just a simple algebraic thing. So I subtract 7.607 from both sides, and I get negative 7.607 equals negative 9.8 t. And then from here, I can divide both sides by negative 9.8, which would give me a positive time because I'm dividing a negative by another negative. As a general rule of thumb, if you're ever in a situation where you solve for a negative time, something has gone horribly, horribly wrong. Okay? The reason why that is because time can't be negative. You're breaking the laws of physics by existing within negative time. Okay? So hopefully none of my live studio audience are existing in negative time because otherwise they would cease to exist and break the fabric of space-time. Okay, I think we're good, right? I think we're good, right? None of us existing in negative space-time, right? Cool. Awesome. Awesome. All right. I guess that does deserve applause. Okay. So if I could do 7.607 divided by 9.8, please. Somebody with a calculator. 0.776. And I need to remember, right now, this is just a number. It means nothing, okay? Without a unit, numbers are meaningless, okay? Here in physics, we are not just a math class. We are a problem-solving class. So I need a unit to put in front of this, or rather behind it. And for time, that is always going to be seconds. So I know it takes, to get to my peak, 0.776 seconds. So this isn't just t. This is 1/2 of my t total. So this is really kind of t 1/2, if you think about it. Okay, this is how long it takes to get to my peak. Now, we want to keep this number in the back of our mind because if we're solving for total height, this is how long it takes for that soccer ball to get to its total height. But if I'm solving for total distance, for example, or total displacement, I want to know the final time, right? How long it takes in total. So I'm going to put this below my t here. Okay, and I'm just going to put kind of t 1/2 equals 0.776 seconds, just so that I have it in the back of my mind. All right, so erasing that, I now have enough information to solve for my displacement in the y direction. And I kind of get my pick of the lot when it comes to these equations, as long as it has that delta x in it. So I'm immediately inclined to look at equation 3. Okay, I usually try to go in order of the equations and kind of go process by elimination. delta x is over here, and technically I have everything I need to solve this, but I don't like the fact that it's not already rearranged for delta x. I like that this one is rearranged for delta x. So I'm going to use that. Again, you could use any of these other equations. You'll get the same answer. So let's do this. So my displacement in the y direction is going to be equal to my initial velocity, which in the y direction was 7.607, times our time, which we're using our half time here because we're just going to the peak right now, 0.776, plus 1/2 a, which is going to be negative 9.8, t squared. So 0.776 squared. Now, this is a lot of numbers here, but thankfully, and actually, do they get cut off a little bit? They do get cut off a little bit, so we're just going to push you a little bit here. There we go. But thankfully, it's just numbers. These are things that we can simplify. So let's start with the first half of our expression here. 7.607 times 0.776. Live studio audience? The one person in the live studio audience is actually doing stuff on their calculator. I want it on the record. All three of the people in the live studio audience have a calculator out. Only one person is actually doing the calculations. Okay? 5.903. Thank you, one person. The other two people are clapping, presumably for her. Okay. 5.903, you said? Okay. So 5.903 plus 1/2 times negative 9.8 times 0.776 squared. We got it? 2.95. Do we agree? Cool. Okay, let me know. The rest of them got their calculators out after I told them to. So, high school seniors, everyone. All right. From here, figuring out delta x is rather simple. Add the two numbers together. Crazy how that works. 8.854. Now, I need a unit on that, right? Meters, very good. Now, is this my total height? Live studio audience is saying no. Why is it not? Tell me why.
Only to the peak.
That is to the peak, yes. So that in theory would be my total height then, wouldn't it?
Oh, shoot.
I need to multiply time by 2. There's a part of the question that you're forgetting right now.
The height is on the hill.
I'm on a hill. I'm on an elevated platform. I have to add 12 to it. Okay, the problem reads, quote, a soccer ball is kicked from the top of a 12-meter hill with an initial speed of 18 meters per second at an angle of 25 degrees above the horizontal. So to determine maximum height, this is how high I make the ball go. But if ground is 0 and I'm kicking it from 12, I need to simply add 12. So when I do that, what do I end up getting? 20.854. Thank you very much. Now, in this case, normally, as my live studio audience mentioned, we'd be able to multiply time by 2, right? That's why we call it time 1/2. And we would be able to get the total time. However, that assumes that we are kicking it from the same height that it's landing from. In this case, we're kicking it from an elevated height, which means it's going to take longer to fall than it will to rise. So we actually can't double our time here. We would instead have to solve for a different time, which is a little annoying, but not anything more difficult than what we're used to. So my total height is 20.854 meters. Now, the last thing I need is this time right here. How long does it take for us to go from our peak down to the ground now? This is more simple than you may think it is. Okay? We are solving for a time again, which is annoying, but because we know that we are starting at an initial velocity of 0, because we're at our peak right now, we know we're accelerating due to gravity, so our acceleration is 9.8. and we know our height is 20.854 meters, we already have enough information to solve for time, yet again using equation 1. So V final is actually unknown right now. So actually we can't use equation 1. My bad. Right? We can use equation 3. Okay. We know X is 20.854. We know VI is 0. We know time is what we're solving for, so this entire term goes away. We know 1/2 is in fact 1/2. Shocking how that works. We know acceleration is 9.8 and t is what we're solving for. We have enough information there. We can plug in and we can solve. So, go give everyone at home a second to screenshot this math if they haven't already. Awesome. So, erasing this. And plugging right back into equation 3. This time we're solving for time to get to the bottom. So, just to clarify what's really going on here, we're taking from an elevated platform, we're going up, and then we're going down. What we've done right now is we have calculated this time. Okay, that's the time that we got to 0.776. As you can see, we have a lot more distance to cover here. Okay, so we need to figure out what this time is. Or not time squared. Trying to do a question mark. Thankfully, we know this total height is 20.854 meters. So using that information, and we also know VI up here is equal to 0. So using all that information, we can actually solve for time here. So let's go ahead and do that. So using equation 3 again, my height, 20.854 equals initial velocity, 0 times time. We don't know that yet. Plus 1/2 a positive 9.8 this time, because now gravity is causing us to speed up as we fall down. So therefore, the acceleration is positive times t squared. Live studio audience, anything times 0, what is that? Thank you, 0. So that just goes away. It is dead. By God, it had a family. So instead, what we can do is we can simplify the rest of this. So 1/2 of 9.8, live studio audience. 4.9, thank you very much. So we are left with 20.854 equals 4.9 t squared. Live studio audience, what should I do next? Divide by 4.9. Say it with confidence.
Divide by 4.9.
Yeah! Probably just peaked the microphone to all God. And applause, yes. When I do that math out, what do I get, live studio audience? With confidence? 4.256 equals t squared. Live studio audience, am I done yet? Why not? I got to square root it. Okay, this is t squared, not t. Okay, that's blasphemous. So I take care of it. Okay, it's like I'm part of the crusade. So when I take the square root of 4.256, what do I get, live studio audience? 2.063. That is how long it takes for my soccer ball to fall to the ground. So I'm going to write that over here. Now, again, we need a unit. That's going to be seconds because it's a time. Now, if I'm thinking about this for a second, in order for me to figure out the total time that it took for it to move forward, what would be my total time here? How would I find that? What do we think, live studio audience? So right now, my live studio audience was not paying attention. Live studio audience, I don't know how live they are actually. Leave a comment down below if you'd be more of a live studio audience than these bozos over here, okay? So, I think they're complaining because I'm technically holding them for lunch right now, but they chose to be here. So, elevated platform. Okay? I know time to go from here to here was 0.776 seconds. I know time to go from up here all the way to down here took 2.063 seconds. How do I figure out how long this whole thing took? Live studio audience, what do you think? Add them together. Very simple. Very correct. Okay. When I do add them together, what do I get? 2.839. Live studio audience, do we agree? Huzzah! So, finally, we can switch over to the blue marker. 2.839, you said? Okay. Finally, I have my total time that this takes, which means that I can finally solve for part E, how far horizontally does the ball travel from the base of the hill. In order to do this, I need to solve for delta x. I know my initial velocity, I know my final velocity, I know my acceleration, I know my time. So there's a few ways I can go about doing this. I think the easiest way would be using, again, equation 3. Delta x is equal to v initial, 16.31, times time by 2.839, plus 1/2 times a, 0, so this whole term goes away, times t squared. So all I'm going to end up doing is just dividing, or actually just multiplying these two things together, and I'm done. So let's go ahead and do that math out. That way we can finally be done with this problem and done with this video. And these run time is already kind of going up on this a little bit. So delta x equals vi times t plus 1/2 at squared. Delta x is what I am solving for. Equals vi is 16.31 times time is 2.839 plus 1/2 0 t squared 2.839 squared. Live video audience, chat, again, any number times 0 is 0. All in unison that time. They're coordinated on that one. So that all goes away. So my final answer is going to be delta x equals 16.31 times 2.839. When I do that math out, please tell me, what do I get?
46.304.
46.304. They're not quite as in unison that time. And what unit does that have to be in? Meters. Bada bing, bada boom. Realest guy in the room. How you doing? 46.304, right? Okay. Now, at this point, I'm actually going to tilt the camera a little bit to get even in better view. When you have this full chart like this, you know for a fact that you're definitely done with this problem. Because there's quite literally nothing else to do here. We've done everything. We have solved the meaning of life. And it was indeed pretty close to 42, if you know what reference that is. So, with that being said, thank you all so much for watching. Thank you so much to my live studio audience. And as always, I will see you all in the next exciting video of Mr. Bell Physics. Make sure to smash that like button. Make sure to hit that subscribe. Ring that bell for notifications. And I will see you all next time.